All right, so this video is going to be all about solutions. And before we get into the calculation side of things, let's just kind of get through a couple of terms. Um, First of all, what is a solution? That basically means you are going to have a homogeneous mixture. So that means you can't necessarily, with your eye, be able to differentiate between what's actually in a mix, what actually is in that mixture. So, um, for example, if let me show you a couple of PETs I have here. If I looked at this solution right here, um, if I added in, let's say this is Kool-Aid drink mix, if I mix that in together, what I'm seeing is just this pinkish liquid solution. I would call that a solution. It's a homogeneous mixture. Those molecules, whatever I've added, my solute has actually dissolved. So I also want to take some time and talk about the difference on what is a solute versus solvent. Um, so the solute is going to be the substance that actually gets dissolved. So basically, I like to think about it as what you're adding to your solvent. So if you think of it in that previous example, the example would be essentially the Kool-Aid mix. That's what you're adding. Now, the solvent is basically going to be the substance that does the dissolving. Most of the time, at least in chemistry, what we'll talk about, water for the most part is going to be the solvent. But you can also mix in other molecules in a non-polar solution. So just know that the solute is what you're adding. There could be more than one thing that's getting added. Solvent is going to be the substance that actually does that dissolving. So if you just kind of revisit these examples, there's always going to be less solute and more solvent present. Otherwise, you're going to get into what's known as a saturated solution. We'll get into that. So let's kind of take a look back at that little animation. When you look at the difference between these, the drink mix, this is my solute. This is just water here. This would be my solvent. So if I just reset this, all this is water. I could even add in more water if I needed to. But again, if I added more, that's my solvent. Okay, down here doing the dissolving, there's my solute. So adding it, I can essentially dissolve it. So, and this is actually adding a solution of already a pre-made drink. So just resetting this, just getting that down. And I can add in all kinds of other stuff too, things like sodium chloride with water. If I added it, it gets mixed in. So again, the solute is what you're adding. The solvent does the dissolving. So that's something that you want to be understanding when you think of solutions. So moving forward, let's look at kind of what this means. What does soluble, insoluble, miscible, and miscible mean? So soluble means that the solute can be dissolved. So for example, if I had sodium chloride and I added that to a beaker of water, it would break up into sodium ions and chlorine ions. So that would be that the solute actually can be dissolved. And you typically you wouldn't be able to differentiate between actually seeing the sodium and chlorine ions. So if it's insoluble, that means the solute essentially can't be dissolved. So basically, if I had a solute, whatever this might be, and I added it to my mixture or my solvent, and it doesn't dissolve, I would say that that is going to be insoluble. Okay. Miscible is going to be where two liquids are soluble. Immiscible is going to be where two liquids are insoluble. So a lot of you guys have seen this example where if I had a water bottle, I have it in my class, and you guys have seen it before, where on one side it's filled with oil, the other one is water, and they're going to be separated out. That's an example of being immiscible. So if you had two liquids that were soluble, they would essentially be mixed together. You wouldn't be able to differentiate between them. But if you had oil, oil is going to get into some properties where oil is non-polar, water is polar. They're going to separate themselves out. But basically, you would get the separation. They're never going to mix together. So but don't limit it just to liquids. This chart kind of goes through all kinds of different examples. If you can actually mix a gas and a gas, nobody can differentiate between the different gases just by looking at it. But there's all kinds of gases that are present. So a lot of people think that the air that you're breathing is primarily oxygen. It's actually not. There's more nitrogen in the air that you breathe in. So we can also mix in gas in a liquid. So you think of a soda, you're trying to put that carbon dioxide gas. Where the solvent is actually the water that you're trying to add that carbon dioxide gas to it. So liquid, really simple example would be like chocolate syrup in the milk. The chocolate syrup is the solute that you're adding to the milk, and that's a nice homogeneous mixture. The Kool-Aid example is really, really common. The solid is the actual powder. That's the solvent. That this S stands for solid. Water is the actual solvent. That's the liquid. And that makes a homogeneous mixture as well. Dental filling, the solute is going to be the I'm going to keep that, sorry. But in terms of this, you're going to actually have also solid and solid. Typically, things like metals are a combination of different solids. So in terms of this, you have carbon, which is going to be the solute added to iron. You heat it, mix it in, that makes steel. So that's a mixture. Now, solvation and aqueous solution, we're going to see this word quite a bit when we get into this chapter. Aqueous means that it's going to be mixed in with water. So anytime you see that AQ in parentheses right after that, that means that water is the solvent that's present. So this just kind of shows you a nice simple overview. Sodium chloride in water, when you mix it in, because water is polar, it's actually going to separate out the ions appropriately. So that process known as solvation is where the surrounding soluble particles with solvent to form that solution. So basically, it's pretty self-explanatory when we get to the intermolecular forces that we talked about last chapter. But this is where we're going to get into a few calculations, but let's kind of get this down first. We have unsaturated solution versus saturated and supersaturated. Unsaturated, where there's less solute than can be dissolved. It means you can always keep on adding solutes. Again, solute is what you're adding. Saturated is going to be where it contains the maximum amount of your solute. And the key thing that I have added here is that any more solute added is going to result in a supersaturated solution. Supersaturated is where there's going to be more than the maximum amount, and you're going to actually see particles at the bottom. But you can actually, if you heat the solution, you can turn a supersaturated solution back into a homogeneous mixture. So a lot of the soda that you drink, for example, is actually a supersaturated solution because you actually have to heat it up. So let me show you the FETs that go along with this one. So if you add it in, let's say I'm adding in some solutes here, nice little sound effects. So according to this, I can't actually form a supersaturated solution. So let me go ahead and reset this. I'm going to decrease my water amount. And if I added a lot of that solute, let's see if I can get a supersaturated solution. No, still can't. Still really saturated. So I'll try one more time. I'll get a really low water amount. I don't even think I can make it here with this solution. So let me go back to this one. I'll go back to the drink mix. If I added a whole bunch of that drink mix here, and I kept on adding it, you're seeing that I am still seeing this drink forming, and all of a sudden right there was saturated. So let me just add a little bit of water here until I get it unsaturated. So right now I would actually call this a saturated solution. Adding any more, it's going to become that super saturated. So you actually, if I kept on adding more, it's tough to see, but if you look at the bottom, I can actually see those solutes still here at the bottom. So again, if I reset this a little bit, it's still saturated. If I added any more, now all of a sudden it's super saturated again. So looking at the definitions here, you just need to differentiate between that. So this is kind of an overview. You have essentially extra water. This is a saturated solution. You're having solids at the bottom. So actually that would be your supersaturated solution where you have your solids here at the bottom. So the key thing here is for the rest of this in terms of concepts is like dissolves like rule. This is big. Polar means that it essentially has a charge due to the unequal sharing of electrons. And if you have a polar solute in a polar solvent, they're actually going to be soluble. So that means if I took something like sugar and added it to water, it's going to be soluble. If I took something like oil and I mixed it in with water, it's telling you that it's insoluble. But if I took oil and mixed it in with another non-polar solvent, it actually would be soluble. So remember that rule, like dissolves like. If it's ionic, something like sodium chloride or all salts for that matter, if you take in something that's ionic and you mix it in with a polar solvent, it's soluble. But if you take salt and you mix it with a non-polar solvent, it's going to be insoluble. So just know the like dissolves like a rule. So understand that. Now, in terms of solubility, just understand how much will dissolve. The maximum amount of solute that will dissolve in a given amount of a solvent. That is what we're going to refer to as solubility. Okay. Now, I just want to kind of recap what are factors that can affect solubility. That's going to be temperature and pressure. Most substances have an increase in solubility with an increased temperature, except for gases. We'll talk about why. But pressure is only going to matter when we think about gases. At high pressures, gases are going to be more soluble. So think of it like you're literally compressing the gases together. At lower temperatures, gases are going to be more soluble. So the lower the temperature, the easier it is for that gas to be soluble. So think of like a cold soda. You're going to have more carbon dioxide at lower temperatures. So understand these two are going to be specific just to gases only. So when you think of pressure, adding in pressure, you're literally forcing those gases together. At lower temperatures, gases are going to be more soluble. So temperature, if you increase it, it's going to increase the solubility. Unless it's a gas. So understand the factors that are going to impact the solubility. So this is just showing you a little graph representation, solubility of a gas of carbon dioxide. So you increase the temperature, the solubility is going to go down. It's the most soluble at lower temperatures. If you have potassium chloride right here, if you increase the temperature, you're actually going to be increasing the solubility. So just know the difference of the factors that impact the solubility. Okay. Other things that impact the rate, so how fast something will dissolve. Again, rate is a measure, not necessarily an amount. So understand that if you increase the heat or the temperature, you're actually increasing the movement, okay, known as your kinetic energy. So these molecules are moving faster and faster. That's going to also break the bonds, making it easier to dissolve, okay? If you are stirring the mixture, you're actually going to increase the amount of these interactions, and it can actually cause it to have some interacting where they actually would do some dissolving. Now, surface area is the one that students struggle the most with. Think of this, if we think about it like the ice, if you had a big ice cube, it's going to take longer. And I don't necessarily want to use ice cubes for this example, but understand that the larger the piece, you're going to have a low surface area. But if you had really, really small pieces, if you actually crunched it up, you're actually increasing that surface area. It's actually going to dissolve faster. So there's a lot of really common labs where, like, if you have like an Alka-Seltzer tablet and you put it in water, it's going to dissolve. But if you crushed up that tablet and then put it in water, it'll dissolve even faster because you're actually increasing that surface area. So that concludes just the basic content of solubility, saturated, supersaturated solution. Next video will be about the calculation side.